Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the Coulomb's law and we will also understand the concept of the electric field intensity. So in the earlier videos, we learned about the basics of the vector algebra and the vector calculus, which are the essential tools for learning the electromagnetic theory. So now, from this video, we will start the electrostatic module. So here, the electrostatics means when the electric charge is at the rest. That means in this module, we will learn the behavior of the electric charge whenever it is in the stationary position. Like what is the electric field that is generated by this charged particle and what is the force that is exerted by this charged particle when any charged particle comes nearby. And we will also understand the concept of the electric potential. And along with that, we will also learn some important concepts. So if you see any stationary charge, then it generates the electric field. And this electric field is typically represented by the electric field lines. So this field represents the space or the region around the charge where any other charge experiences the force. And this electrostatic force that is experienced by this charge can be explained using the Coulomb's law. So as per this Coulomb's law, if we have two stationary charges Q1 and Q2, then the electrostatic force between them is directly proportional to the product of the Q1 and Q2 and it is inversely proportional to the square of the distance between the two charges. So we can say that here this F is proportional to this Q1 times Q2 divided by R square. And further it can be written as this K times this Q1 times Q2 divided by R square, where this K is the proportionality constant. And it can be given as 1 divided by this 4 pi times epsilon naught, where this epsilon naught is the permittivity of the free space. So basically, this permittivity represents the ability of the free space to permit these electric field lines. And its value is equal to this 8.854 times this 10 to the power minus 12. That means here we are assuming that the two charges are in the free space. But suppose if the charges are not in the free space and they are in some medium, then of course the expression of the force will remain the same. But now this constant K will also have this relative permittivity. And the value of this relative permittivity is the medium specific. So that is the only change we will have in the expression when the two charges are in the specific medium. So now, while finding this electrostatic force, we also need to consider the sign of these charges Q1 and the Q2. So as we know, the like charges repel with each other. That means if both charges are positive or the negative, then there will be a repelling force between the two charges. And in that case, this Q1 times Q2 will be positive. And due to that, as per this expression, the force F will be also have the positive value. On the other hand, the unlike charges attract each other. That means if one charge is positive and the other charge is negative, then they will attract each other. And in that case, this Q1 times Q2 will be negative. So accordingly, we will also have the negative sign in the expression of the force. So now, if you see this electrostatic force or this Coulomb's force, then it is the vector quantity. That means along with the magnitude, it will also have the direction. So now let us see mathematically how it can be represented. So from the origin, if the Q1 is located at the distance R1 and if the Q2 is located at the distance R2, then the force acting on this charge Q2 due to this charge Q1 can be given as F12. And this force acts along the line that is joining the charge Q1 and the Q2. So if you see the direction of this charge, then it can be given by the unit vector along this direction. So here, since the O represents the origin, so if we draw a vector from the origin towards the charge Q1, then that will be the position vector. Likewise, here this R2 will also represent the position vector. That means if this R1 and R2 are the position vectors, then the vector in the direction of the Q1 to Q2 is equal to R2 minus R1. So if we divide this vector by its magnitude, then we will get the unit vector in the direction of the charge q1 to q2. Let's say that is equal to a12. And if we see the distance between the charge q1 and q2, then that is equal to the magnitude of this vector r2 minus r1. So we can say that the force F12 is equal to 1 divided by 4 pi times epsilon naught times this q1 times q2 divided by r square. And here this r square is equal to the distance between the charge q1 and the q2. So in this case that is equal to the magnitude of this r2 minus r1 whole square. And if we see the direction of this force, then it can be given by this unit vector. So that is equal to this r2 minus r1 divided by the magnitude of this r2 minus r1. So in this way, this expression represents the force between the two charges along with the magnitude and the direction. So this force is the force that is acting on the charge q2 due to the q1. Now here, if you see this Coulomb's force, then that is the mutual force. That means if we find the force that is acting on the charge q1 due to the charge q2, then it will be of the same magnitude but will be in the opposite direction. That means here, if we see the force that is acting on the charge q1 due to this charge q2 or this F21, then it is the exactly same but in the opposite direction. So from this, we can say that here this F21 is equal to minus F12. Or more precisely, here this unit vectors A12 is equal to minus A21. So we can say that the Coulomb's force is the mutual force between the two charges, and the force that is experienced by the one charge due to the other charge will be of the same magnitude, but their direction will be opposite. So now, this Coulomb's law is also applicable when we have the more than two charges. So for example, when we have three charges, then the force acting on the one specific charge can be found using the principle of the superposition. For example, let's say we have three charges q, q1 and the q2. So here the force acting on this charge q due to this charge q1 and q2 can be found using the superposition principle. That means here the total force that is acting on this charge q is the summation of the F1 and the F2, where this F1 represents the force due to the charge q1 while this F2 represents the force due to q2. So here once again this O represents the origin, and here this R1 and R2 are the position vectors for this charge q1 and q2, and similarly this R represents the position vector for this charge q. So based on that, if we see the force that is acting on the charge q due to this charge q1, then it can be given as 1 divided by 4 pi times epsilon naught times q times q1 divided by r square. And here the distance between the two charges is equal to the magnitude of this r minus r1. And here the unit vector in the direction of this force is equal to this r minus r1 divided by its magnitude. So that is why here in the denominator we will have the magnitude of this r minus r1 whole cube. So along with the unit vector, this is the expression of the force F1, and likewise this is the expression of the force F2. That means the overall force that is acting on the charge q is the summation of the force F1 and the F2. So in general, if we have n charges, then the total force that is acting on the charge q can be found using the superposition principle, where here this r1, r2, r3 up to rn represents the position vectors. So now let us understand the concept of the electric field intensity. So we have seen that any electric charge generates the electric field. So this electric field intensity represents how strong the electric field is there at the given location. So to measure that, a test charge qt is moved in the electric field of the charge q. So as you know, anywhere in this electric field, this test charge will experience the force that is associated with this charge q, and this force can be given by this Coulomb's law. So here this electric field intensity is the force per unit charge. That means if we divide this force with the test charge, then we will get the force that is experienced by this unit test charge because of this charge q. So basically, this expression represents the intensity of the electric field at the specific location irrespective of the magnitude of the test charge. So as you can see, this electric field intensity is proportional to the magnitude of this charge q, and it is inversely proportional to the square of the distance. That means as we move away from the charge, then the electric field intensity will get weaker. So similar to the electrostatic force, this electric field intensity is also vector quantity. That means it has both direction as well as the magnitude. And this electric field intensity can be also expressed when we have a more than two charges. So for example, if we have a three charges, that is q1, q2 and the trace charge qt, then the total electric field intensity at the location of this trace charge qt can be found using the superposition principle. That means the total electric field intensity at the location of this charge qt is equal to the electric field intensity due to the charge q1 plus the electric field intensity due to the charge q2. So as you can see, the expression of this electric field intensity is similar to the expression of the force, but here it will get divided by the value of the test charge. So in this way, using the principle of the superposition, even if we have n charges, then also we can find the electric field intensity due to all these charges at the location of the test charge. So now, to understand it more clearly, let us take one example and let us see how to find the electrostatic force and the electric field intensity. So in this question, we've been given the 2-point charges of 1 millicoulomb and the minus 2 millicoulomb, and they are located at the given locations. So here, we've been asked to find the electrostatic force that is acting on this 5 nanocoulomb charge, which is located at the given location. And here, we've been also asked to find the electric field intensity at the same location. So here, we can find this electrostatic force by using the Coulomb's law. And here, since we have the two charges, so we will use the superposition principle. So as per the Coulomb's law, this is the net force that is acting on the 5 nanocoulomb charge, where here this r is the position vector for this 5 nanocoulomb charge, and similarly this r1 and r2 are the position vectors for this 1 millicoulomb and the minus 2 millicoulomb charge. So here, since the r is located at the location of 0, 3, 1, so we can say that its position vector is equal to 3ay plus az. Similarly, if we see the position vector r1, then that can be given as this 3ax plus 2ay minus az. And likewise, this position vector r2 for this 2 millicoulomb charge is equal to this minus ax minus ay plus 4az. So we can say that over here this r minus r1 is equal to the subtraction of these two position vectors, and that is equal to minus 3ax plus ay plus 2az. That is the subtraction of these two position vectors. And likewise, if we see this r minus r2, then that is equal to the subtraction of these two position vectors. So that is equal to ax plus 4ay minus 3az. So here, the distance between the charge q and the q1 can be given by the magnitude of this vector. So that is equal to the magnitude of this r minus r1. And as you know, it can be given as the square root of minus 3 whole square plus 1 whole square plus 2 whole square, and that is equal to square root of 14. So likewise, if we find the magnitude of this r minus r2, then that is equal to square root of 1 square plus 4 whole square plus minus 3 whole square, and that is equal to square root of 26. So now in the above expression, let us put the value of this vector r minus r1 as well as the r minus r2. And apart from that, let us also put the value of the distance between the two charges. But before that, if you see, then in the both terms, this 1 divided by 4 pi times epsilon naught is common. So first of all, let us take it outside. And now, if you put the value of this vector r minus r1 and the r minus r2, then the net force can be written like this. So as we have seen, this term is nothing but the 14. So we can say that is equal to 14 to the power of 3 by 2, or it can be written as 14 raised to 1 plus 1 by 2. So that is equal to square root of 14 times 14. Likewise, this term can be written as square root of 26 times 26. So let us put all these values and let us further simplify it. So if we further simplify it, then it can be written like this. So now in this expression, let us put the value of the 1 divided by 4 pi times epsilon naught. So as we have seen, the value of the epsilon naught is equal to 8.854 times this 10 to the power minus 12, or approximately it can be written as 1 divided by 36 pi times this 10 to the power minus 9. So here for the simplicity, we will use this approximation. So if we put the value of this epsilon naught as 1 divided by 36 pi times 10 to the power minus 9, then we will get this 9 divided by 10 to the power minus 9. So over here, this 10 to the power minus 9 will get cancelled out. So now, if we further simplify it, then this 9 times this term is equal to 0.859. And likewise, this 9 times this term is equal to 0.678. So if we further simplify it, then the net force is equal to minus 3.255 times AX minus 1.853 times AY plus 3.752 times AZ. And of course, over here, we will also have this 10 to the power minus 3. So as you know, the unit of the force will be equal to Newton. And considering this factor, we can say that the overall force is in the millinewton. So in this way, we found the net force that is acting on the 5 nanocoulomb charge. So here in the question, we will also ask to find the electric field intensity at the same location. So here, if we divide this force by the 5 nanocoulomb, then we will get the electric field intensity at the location of the 5 nanocoulomb. So we know that this force F can be given by the following expression. So now, to find this electric field intensity at the same location, let us divide this force by the 5 nanocoulomb charge. And if you further simplify it, then this electric field intensity is equal to minus 651 times AX minus 370.6 times AY plus 750.4 times AZ. And here, the unit of this electric field intensity is the kilovolt per meter. Because here, after the division, we will also have the factor of the 1000. So this is the net electric field intensity at the location of the 5 nanocoulomb charge. So in this way, using the Coulomb's law, we can easily find the force that is acting between the different charges. And we can also find the electric field intensity due to those charges. So in our day-to-day life also, we are experiencing this electrostatic force. And in many applications also, the same principle is used intentionally. For example, in many factories and the power plants, the electrostatic precipitator works on the same principle for the air pollution control. So in these systems, the smoke particles are passed through the high electric field. So due to this high electric field, the smoke particle gets negatively charged. And now, these negatively charged smoke particles are attracted towards the positively charged plates. So here, due to the Coulomb's force, these unlike charges are getting attracted to each other. So in this way, the dust and the smoke particles are getting removed and they are being prevented from coming out of the exhaust. So similarly, the same electrostatic force also works in the laser printer. So in the laser printers, if you see, then we have the drum. So initially before printing, by applying the high voltage, this drum is charged negatively. And now using the laser, the part where we want to form the image, from those part, these negatively charged particles are removed. So in these printers, as you know, the toner is used for the printing. So this toner is also negatively charged. So now, when this toner is applied to the drum, then the negatively charged particles of the toner and the drum repels with each other. And these toner particles sits on the places of the drum where there is a no charge. So basically, they will sit at the places where we want to create the image. So now, once the toner particles sets on the drum at the desired location, then the paper is passed between the drum and the roller. So here if you see, then this roller is the positively charged. So here, what happens? The positively charged particles of this roller attracts the negatively charged toner particles. And in this way, these toner particles gets attracted towards the paper. So here, because of the Coulomb's law or the electrostatic force, the opposite polarity charges are getting attracted to each other. And in this way, these toner particles are coming on the paper. So finally, the paper is passed through the heated roller, and in this way, the toner is melted and it gets permanently fused in the paper fiber. And in this way, the print gets formed on the paper. So as you can see, these electrostatic charges and the force that is acting between them plays the crucial role while printing using these laser printers. So these are some real world applications where we can see that this electrostatic force between the charged particles is playing the crucial role. So I hope in this video you understood the concepts of the Coulomb's law and the electric field intensity. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.